Come on my dears, let us proceed further in chapter number 3. We now go for question number 6 about mobility of a charge carrier. Mobility of a charge carrier. Fine. Now tell me, do you know the different media in which electrical conduction takes place? They are metals, semiconductors, then electrolytes and ionized gas, correct? Now let us see in these different media which are the different types of charge carriers. First of all, we talk about metals. They are called good conductors of electricity. They have their charge carriers in the form of free electrons. Okay, fine. So here I have written metals have charge carriers in the form of free electrons, correct? Then which are called semiconductors, the elements which have electrical conductivity smaller than that of good conductors and more than that of insulators. They are called semiconductors, correct? In the chapter of electronics in 4th semester, you will be taught about conduction of electricity in semiconductors. And there you will come to know that inside the semiconductor, electrical conduction takes place through two different types of charge carriers. First is free electrons and second is holes. What are called holes and how does electrical conduction takes place with the help of holes, that you will be taught in chapter of electronics in 4th semester. Okay? At present you just remember the name of charge carrier, that is holes. So I written here for semiconductor, come on, free electrons and holes, they are the charge carriers. Okay? Fine. Then what do you mean by electrolyte? If any solid substance is getting completely dissolved in some liquid, then that solid substance is called solute, that liquid is called solvent, and the mixture of solute and solvent is called solution, that you must be knowing from chemistry. Now that particular solution which conducts electricity is called an electrolyte, okay. In the same chapter, we will study how electrical conduction takes place in the electrolyte, and there we will study it takes place in the form of two types of charge carriers. One is positive ions, second is negative ions. Okay. So inside the electrolyte, the conduction of electricity takes place through positive and negative ions. Please remember. And the last medium, that is ionized gas. Inside the ionized gas, the conduction of electricity takes place through electrons and positive ions. Okay. Don't write here free electrons, write only electrons and positive ions. Okay, fine. Now, though electrical conduction takes place through different media with the help of different charge carriers, we find that different types of charge carriers, they have got different speed while conducting the electricity, and thereby we require to just have comparison between their speeds. And for that purpose, we have defined a physical quantity called mobility of a charge carrier. How it is defined? Let us see now. Last time we had studied about two different formula for electric current density. Remember, capital J was equal to NEVD, correct? And second formula was sigma into E. Just give me identification of each symbol. Capital J means electric current density, small n means free charge carrier density, that is number of free charge carriers in the unit volume. What about E? Magnitude of charge of one electron. Vd is the drift velocity. Okay. Sigma is electrical conductivity and capital E is the electric field inside the given medium. Okay, fine. Now, when you compare these two, you can find out Vd upon E, and that will be equal to sigma upon Ne, correct? Tell me, what does this ratio give to us? It gives us drift velocity of a given charge carrier per application of unit electric field, and the same ratio is known as mobility of that charge carrier, shown by symbol mu. So, how will you define it now? Very simple. The drift velocity achieved by a given charge carrier per application of unit electric field is called its mobility, shown by symbol mu. Correct? Fine. In short, drift velocity per 1 unit electric field is called mobility. Fine. And now Vd upon E is nothing but sigma upon n into E. Sigma upon n into E. Correct? Just give it equation number 2. Now from the same equation, we can find out the SI unit of mobility of a charge carrier, and that will be ratio of SI units of velocity and electric field. Come on, for velocity, what is the SI unit? Meter per second. For electric field, it is volt upon meter. Correct? Fine. Now this meter will go up, second will come down. So meter into meter, that is meter square upon volt into second. Volt into second. Correct? Meter square upon volt into second. Now let us obtain another equivalent SI unit of mobility of a charge carrier this way. Come on, meter square as it is. Correct? Upon volt into second as it is. From here we start. Now this meter square as it is. What is volt? 1 volt is 1 joule per coulomb. So volt is replaced by joule upon coulomb. Second as it is. And now tell me, this coulomb will go up. So it is now coulomb into meter square. Coulomb into meter square upon joule into second. Joule into second. But don't you know, I equals to Q by T, current equals to charge upon time. If you write SI units, then ampere equals to coulomb upon second. So coulomb upon second can be replaced by ampere. Meter square as it is upon joule as it is. Correct? Now in the next chapter, we will study about magnetic field, and its SI unit is Tesla. You can prove that this unit is just equal to reciprocal of Tesla. This unit is equal to 1 upon Tesla. That is what you can prove. Okay? In chapter number 4, we will prove it. Okay? Fine. What about dimensional formula of mobility of a charge carrier? From here you can write down. For ampere, it is A raised to 1. For meter square, it is L raised to 2. For joule, that is for work, you must remember the dimensional formula. M raised to 1, L raised to 2, T raised to minus 2. So M raised to 1, L raised to 2, T raised to minus 2. Correct? Fine. And now this M raised to 1 going up will become M raised to minus 1. Come on, L raised to 2 from the numerator and from the denominator getting cancelled. This T raised to minus 2 will go up, will become T raised to plus 2, A raised to 1 as it is. M raised to minus 1, T raised to 2, A raised to 1. Okay? That is the dimensional formula for mobility of a charge carrier. Got it? My dears, please remember, if you change the system of units, then for the same physical quantity, unit will get changed, but its dimensional formula will remain unchanged. In all the unit systems, remember, dimensional formula of a given physical quantity remains as it is. Correct? So dimensional formula does not depend on the type of unit system, but the unit depends on the type of unit system. Okay? Fine. Now from equation 2, just make subject of the equation, that is sigma. Find out sigma from here, take this up. So sigma will be n into E into mu. Sigma equals to n into E into mu. Correct? Fine. Now let us talk about semiconductors. For semiconductors, just now we have seen the conduction of electricity takes place through two types of charge carriers. Come on, free electrons as well as holes. Correct? So let us find out the corresponding electrical conductivity. For free electrons, instead of sigma, you may write sigma E. You may write in place of n, you may write Ne, and in place of mu, you may write mu E. What do you mean by Ne? Free electron number density, that is number of free electrons per unit volume. What is mu E? That is mobility of free electrons. Got it? Similarly, for holes you can write here, instead of sigma E, you may write sigma H, instead of Ne, you may write NH, instead of mu E, you may write mu H. Okay? This NH means hole number density, that is number of holes per unit volume. And why you are writing E as it is? In the chapter of electronics, you will be taught that whenever there is a conduction of electricity in semiconductor in the form of holes, you can just consider the conduction of electricity in the form of bound electrons in just opposite direction. So, conduction of electricity through holes is as good as conduction of electricity through bound electrons, but the difference is they just flow in opposite direction. Okay? So, here also the conduction takes place through bound electron, and for bound electron also magnitude of charge of one bound electron is E only. So, I am writing here also E, correct? Fine. What will be my NH? As I told you, hole number density, and here mu H means mobility of holes. Got it? Now, if you want to find out total electrical conductivity in a semiconductor, then you must add this to partial values of electrical conductivity. That is sigma E plus sigma H, sigma E plus sigma H, that is this plus this. So, it will be now this plus this, correct? And when you take this plus this, what part you can take common? Small e, if you take common, inside the bracket Ne into mu E plus NH into mu H, correct? So, using this formula, you can find out total electrical conductivity in a semiconductor. Got it? We now go for question number 7 about relation between resistivity and temperature. Relation between resistivity and temperature. Let us talk about this relation for 3 different media. First is metals, that is good conductors. Then we will talk about semiconductors, and then we will talk about alloys. Okay? Let us see one by one. First of all, for metals. For metals, the relation between resistivity and temperature is established experimentally. And for that, what we do, we just keep a given metal at different temperatures. Each time we measure its resistivity practically, and then after, by making some mathematical adjustment on the basis of trial and error, we just obtain a formula showing relation between resistivity and temperature. But that formula should be such that in which when we put up different temperature values and when we calculate corresponding resistivities, those resistivity values must come out to be exactly equal to those values which are obtained practically. Okay? So, that formula which is obtained mathematically, which is quite consistent with practically obtained results, that formula is known as empirical formula. And that empirical formula for showing relation between resistivity and temperature for metals is this: rho 2 equals to rho 1 into bracket 1 plus alpha into theta 2 minus theta 1, correct? My dears, please remember, every empirical formula is just obtained only on the basis of mathematical adjustments and practically obtained observations. Okay? It is never derived using any principles of physics. Okay? Fine. Now, this formula showing relation between resistivity and temperature for metals is true only for small intervals of temperature, only for small range of temperature. Okay? Now, let me give you identification for each symbol. What is theta 1? It is some reference temperature. Okay? And theta 2 is another temperature which is close to this reference temperature. In short, I mean to say this temperature difference is small. Okay? Rho 1 is the resistivity of a given metal at this reference temperature. Rho 2 is the resistivity of the same metal at another temperature theta 2. Okay? Then what is alpha? It is called temperature coefficient of resistivity. Temperature coefficient of resistivity. Got it? Fine. Now, in textbook, you will not find the definition of alpha. Let us obtain now definition of alpha. Just transfer this rho 1 here. So, rho 2 upon rho 1, and this 1 you can transfer here will become minus. Rho 2 upon rho 1 minus 1. Rho 2 upon rho 1 minus 1. Correct? And that will be equal to alpha into theta 2 minus theta 1. Alpha into theta 2 minus theta 1. Correct? And now transfer this rho 2 minus rho 1 upon rho 1. and that will be equal to alpha into theta 2 minus theta 1 as it is. Tell me, what is this rho 2 minus rho 1? Change in the value of resistivity. Let it be delta rho, correct? This is the initial value of resistivity or original value of resistivity. Let it be shown by symbol rho. So, rho 1 is replaced by rho, and here alpha as it is. What about theta 2 minus theta 1? It indicates some temperature difference. Let it be delta theta. Okay, fine. Now, find out alpha from here. It will be delta rho upon delta theta, correct? Fine. Here these changes are supposed to be small. Now, if the changes are very small, differentially small, substantially small, then in the language of calculus, we write the same right hand side like this now. D rho upon d theta. Instead of delta rho, you may write d rho. Instead of delta theta, you may write d theta, correct? Fine. Now, using this, let us define now alpha. What do you mean by alpha? Temperature coefficient of resistivity. Now, in this formula, if you take delta theta, say 1 degree centigrade, then just put it here 1 degree centigrade, then alpha will be just delta rho upon rho. Alpha will be delta rho upon rho, correct? Change in any physical quantity divided by its original value will always give you fractional change in that physical quantity, or you can say partial change in that physical quantity. Okay? So, this will give me partial change in the resistivity or fractional change in the resistivity, and the same is known as alpha, that is temperature coefficient of resistivity. Now, using this fact, you can define alpha this way, very simple. Fractional or partial change in the resistivity of a given metal per 1 degree centigrade change in its temperature is called its temperature coefficient of resistivity. Once again, the fractional or partial change in the resistivity of a given metal per 1 degree centigrade change in its temperature is called its temperature coefficient of resistivity, shown by symbol alpha, correct? What about unit of alpha? You can find out from here. Come on. Resistivity upon resistivity. So, this fractional change in resistivity will not have any unit, and now it is 1 upon temperature. So, what should be the unit of alpha? Simple, 1 upon degree centigrade, that is degree centigrade inverse, here it is, or 1 upon Kelvin, that is Kelvin inverse, correct? And remember, value of alpha will be same in these two units, because this is not temperature, it is change in temperature. And change in temperature, if you measure in degree centigrade or in Kelvin, comes out to be same. Okay? So, remember two units for alpha, one is degree centigrade inverse and another is Kelvin inverse. Okay? Let us see now graph of resistivity versus temperature for metals. It is obtained practically of this nature, graph of resistivity versus temperature. The nature of the graph is like this. Correct? Tell me, how do you find this graph? For the temperatures around room temperature, the graph is a straight line graph. That is, the relationship between resistivity and temperature is linear relationship, correct? And for the temperatures which are quite low as compared to room temperature, and for the temperatures which are very high as compared to room temperature, we get the graph of rho versus theta to be curved graph. And that curved graph indicates the non-linear relationship between resistivity and temperature. Okay? Tell me, in all, what do you notice in the graph? As temperature is increased, come on, resistivity increases. Correct? No matter whether it increases linearly or non-linearly, no matter, one thing is certain, when temperature is increased for a metal, its resistivity definitely increases. Correct? So, when temperature is increased, resistivity is also increasing. What does it mean? Mathematically, d rho upon d theta will be positive, because when temperature is increasing, resistivity is also increasing. Okay? Now, find out d rho upon d theta from here. Take this rho down, okay, and that rho you can take here. So, d rho upon d theta will be alpha into rho. d rho upon d theta will be alpha into rho. I have written here, d rho upon d theta will be alpha into rho. So, this d rho upon d theta is nothing but alpha into rho, and if it is positive, then this product is positive, but rho is positive, so alpha has to be positive. So, remember, for metals or for good conductors of electricity, the temperature coefficient of resistivity is positive. Okay. What about the range of values of resistivity for metals at room temperature? It is found to be ranging from 10 raised to minus 8 ohm into meter to 10 raised to minus 6 ohm into meter. Whenever you express any range, you must express first of all its a minimum value and then after maximum value. Minimum resistivity of metal on average at room temperature is found to be 10 raised to minus 8 ohm into meter. Maximum resistivity of metals at room temperature on average is found to be 10 raised to minus 6 ohm into meter. Correct? Fine. Then we go for semiconductors. For semiconductors, if you obtain a graph of resistivity versus temperature, is found to be like this. Correct? Fine. What does it indicate? As temperature is increased, come on, resistivity goes on decreasing. Correct? Fine. Temperature is increased, resistivity decreases. Okay. So, d rho upon d theta will be negative, because when theta increases, rho decreases. That is why. Replace now d rho by d theta by alpha into rho. Replace it here. D rho upon d theta is nothing but alpha into rho, and that is negative. When this product is negative, and in that we know that rho is positive, so alpha must be negative. So, remember, for semiconductors, the temperature coefficient of resistivity is negative. Correct? For metals it was positive, for semiconductors it is negative. Now, let us talk about alloys. In laboratory, we have prepared certain alloys out of some metals such that their resistivity should remain constant, though we change the temperature drastically. For very big changes of temperature also, the resistivity should remain constant. Such alloys we have prepared in laboratory. They are, please remember the names, nichrome. It is an alloy made up of nickel, chromium and iron. Nickel, chromium and iron. Another is manganese. Another is manganese. It is made up of manganese, nickel and copper. Manganese, nickel and copper. Third is constantan. It is made up of two metals, copper and nickel. Copper and nickel. Okay. Now, if you obtain a graph of resistivity versus temperature for these alloys, we find that graph is almost horizontal. Correct? And what does it indicate? Though you are increasing the temperature or you may decrease the temperature, this resistivity value will remain almost constant. Okay? The graph is not perfectly horizontal, it is slightly increasing, correct? Having some positive slope, but the slope is very small, it is almost horizontal. So, for a large change in temperature, resistivity is almost constant, and that is why the wires used in Western bridge, wire used in potentiometer and the wire used in making rheostat, we just prepare out of such alloys. Okay. Then what is the benefit? Benefit is that though you may perform experiment in the winter season or in the summer season, though there may be large change in temperature, your final result will remain almost unchanged. Okay. Fine. That is what I have written here also. Though theta is increased or decreased, come on, resistivity remains almost constant. Then what will be d rho upon d theta? Though you are increasing the temperature or you may decrease the temperature, then resistivity remains almost constant. Then don't you know mathematically, derivative of a constant function is 0, correct? So, I am writing here 0, and what is the formula for d rho upon d theta? It is alpha into rho. So, when d rho upon d theta is alpha into rho, and right now it is 0, but resistivity is not 0, so alpha must be 0, correct? So, alpha is nearly 0 for alloys, correct? So, for alloys, temperature coefficient of resistivity is nearly 0. For metals, it is positive, and for semiconductors it is negative, correct? Fine. Then what do we find in practice? That the elements which are insulators of heat, they are also found to be insulators of electricity. Have you remembered from 11th standard the examples of insulators of heat? You must remember it is wood, then glass, then paraffin, then wax, then paper, then glass, bakelite, correct? All these substances are insulators of heat. They are also insulators of electricity, but there is one exception, and that is about superconductor. Here I have written superconductor is an exception. What is superconductor? What is superconductivity? We will study in question number 10. At present, you remember that generally it is found that those elements which are insulators of heat, they are also insulators of electricity. Okay? So, thermal insulators are also electrical insulators, but the exception is superconductor. Okay? It is an exception. What about values of resistivity for electrical insulators? It is very high resistivity. It is 10 raised to 18 times than these values. 10 raised to 18 times than these values. When you multiply by 10 raised to 18 here, it will be 10 raised to 10 ohm into meter. When you multiply 10 raised to 18 here, it will be 10 raised to 12 ohm into meter. 10 raised to 10 ohm into meter to 10 raised to 12 ohm into meter. So, resistivity of insulators is nearly 10 raised to 18 times the resistivity of metals. Okay. Let us go for now next question about resistor and its types. Any electrical element which has the property of electrical resistance is said to be electrical resistor. Okay. A circuit component which has resistance is called resistor. How do you show that resistor in the circuit diagram? Symbolically, it is this symbol. This is the symbol for showing presence of resistor in a circuit. Okay. And you must have remembered the property electrical resistance I defined in the previous lecture. Remembered the specific property of material of a conductor whereby it opposes the drifting motion of charge carriers inside it is called its electrical resistance, and a circuit element having property of electrical resistance is called electrical resistor. Okay. And its a circuit symbol, as I said, it is like this. Okay. With its resistance we should show here, that is by symbol R. Okay. There are three types of resistors we use in practice. First is wire wound resistors. Wire wound resistors. In that what we do, on a proper insulated base, we just wind the wires made up of these alloys, correct? And thereby we prepare the resistors which are called wire wound resistors. Okay. And because for alloys, for these alloys just now we have seen the temperature coefficient of resistivity is nearly 0, then the resistivity will remain almost constant. Okay, fine. Then secondly, we also use very widely this type of resistors called thin film resistors in the electronic circuits. Okay. Then other type of resistors we use normally majority in the electronic circuits, it is carbon resistors. Carbon resistors. Now, in our syllabus we have to study this carbon resistors quite in detail, correct? Why carbon resistors are used very widely in the electronic circuits? There are 4 advantages which we have with carbon resistors. Which are the 4 advantages? First, they are smaller in volume, lighter in weight. When the resistors themselves are smaller in volume and lighter in weight, naturally any device, any instrument made out of such elements will be also very small in volume and quite light in weight, and that is why that instrument, that device, you can make it portable, correct. So, all these portable devices are made up of these elements. The credit goes to these carbon resistors. They are small in volume and lighter in weight. Fine. Then second, they are quite cheap in the cost. The carbon resistors available in market, they are found to be quite cheap. Cost wise, they are very cheap. Then they are quite reliable. During the normal usage of these resistors, their resistance is found to be remaining almost constant. So, they are quite reliable, quite trustworthy. Okay. Then number 4, they are available in a very wide range, right from small value, say as small as 1 ohm, to the very big value of resistance, say 100 mega ohm. The resistors are available in the market in the form of carbon resistors. The range of availability is very wide range. It is from 1 ohm to 100 mega ohm. 1 mega means 10 raised to 6. Okay. Now, let us see completely all the things in detail about carbon resistors in the short note in question number 9. Come on. Short note on carbon resistors. Short note on carbon resistors. First of all, let us see how it is being prepared in the laboratory. For preparing carbon resistor, first of all, we take a mixture of 2 materials. First is pure graphite. It is like a good conductor. It is a good conductor. And another material is called resin, which is a bad conductor or insulator. Correct? Depending upon the value of resistance, we just select the proportion of these 2 materials. For example, if you want very high value of resistance, then you should add more amount of resin and less amount of pure graphite. If you want quite small resistance, then you should add more amount of pure graphite and less amount of resin. Simple? Fine. So, depending upon the value of resistance required, you may add these 2 materials in a definite proportion, and then after we prepare the mixture, and then we apply very high pressure on that mixture, and we just give it a shape of a cylindrical stick, and that stick I have shown here. Correct? And then after we apply a layer of non-conducting material on its surface. That layer I have shown with the blue color. Okay. And then after we just want to connect this resistor in the circuit, and for that we just fix up 2 copper wires mixed with tin. Such 2 copper wires are fixed at the 2 ends, with the help of which we can just make it soldered in the circuit for permanent connection. Okay. And then after we would like to show the value of resistance of this carbon resistor in ohms, and for that we have adopted one method which is accepted internationally, which is called color code. And according to that color code, we just print either 3 or maximum 4 number of color bands on its surface. My dears, here you please remember one thing. If a 4th colored band is there, it is far from this 3rd band. Correct? Distance between 3rd and 4th, it is maximum. Okay? You should keep that 4th band on the right hand side, and then after you should determine the order of colors from left hand side. Okay? In a given typical carbon resistor, suppose the order of colored bands is starting from left, it is suppose yellow, violet, orange and silver. If it is so, then how would you determine its value of resistance in ohms according to that method which is known as color code, which is accepted internationally? I am showing you. Now, my dears, let us find out the value of resistance of this particular carbon resistor in ohms, okay, according to color code. But remember the standard method to express the value of that resistance. That standard method is this: R equals to xy into 10 raised to n plus or minus q. Now, don't get confused. This is not x into y. This is not a product of x and y. No, it's not x into y. It is a 2-digit figure. 2-digit figure. Okay. In this 2-digit figure, if you just compare it with 47, then you can understand this y is the digit of units and this x is the digit of tens. Y is the digit of units, right now it is 7, and x is the digit of tens, right now it is 4. Okay. So, remember, in this 2-digit figure, y is the digit of units and x is the digit of tens. Okay. And this 2-digit figure is to be multiplied with 10 raised to n, and then after plus or minus q. What does this Q indicate? Q value indicates the tolerance of a given carbon resistor. What do you mean by tolerance? Tolerance value indicates the possible variation in the value of resistance during the normal use of that resistor. Okay? So, tolerance gives you amount of variation in percentage. Okay? Fine. Now, how to determine these values? I am showing you. Just go this way. 1, 2, 3, 4. 1, 2, 3, 4. Okay? Value of X is to be determined from the color of first band. Value of Y is to be determined from the color of second band. Value of 10 raised to n is to be determined from the color of third band. And value of Q is to be determined from the color of fourth band. Okay? That's why I said 1, 2, 3, 4. Now, let us find out these values for this particular carbon resistor by following this whole color code. Okay? Fine. Here I have written different colors. You can just read black, brown, red, orange, yellow, green, blue, violet, grey, white, golden, silver and none. If fourth band is not there, then okay. Come on. For these colors, the corresponding digits I have written here, starting with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Then corresponding values of 10 raised to n I have written here. Starting from 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, 10 raised to 4, 10 raised to 5, 10 raised to 6, 10 raised to 7, 10 raised to 8, 10 raised to 9. Then for this golden color, remember it is 10 raised to minus 1. For silver color, it is 10 raised to minus 2. Okay. Then the tolerance is to be decided by the color of fourth band, and if color of fourth band is brown, then tolerance is plus or minus 1%. Then for red color, plus or minus 2%. For orange color, plus or minus 3%. For yellow color, plus or minus 4%. For golden color, plus or minus 5%. For silver color, plus or minus 10%. And if fourth band is not there, then tolerance is maximum, plus or minus 20%. When tolerance is maximum, then you can say amount of variation in the value of resistance would be maximum, meaning thereby that resistor is not reliable because its resistance changes drastically. Okay? Remember, a carbon resistor having maximum tolerance is said to be lowest in the quality. Quality wise it is lowest because its resistance changes drastically. Okay? And that carbon resistor which has minimum tolerance, it is said to be highest in the quality, and that is if fourth band is with brown color, then there is a minimum tolerance only 1%. Okay? That is quality wise the best quality. Fine. Now, for this carbon resistor, tell me what is the first color? First color is yellow, correct? Value of X is to be determined from the color of first band. Color of first band is yellow, and for yellow, look here, for yellow it is digit 4. That's why below X I am writing 4. Value of Y is to be determined from the color of second band. Color of second band is right now violet, and for violet color the digit is 7. So below Y you should write 7, correct? Multiply by 10 raised to n. But the value of 10 raised to n is to be determined from the color of third band. Color of third band is orange. And for orange, come on, it is 10 raised to 3. So I am just multiplying by 10 raised to 3. That many ohm plus or minus Q. What is Q? Tolerance. Its value is to be determined from the color of fourth band. And color of fourth band is right now silver. And for silver color, come on, it is plus or minus 10%. Come on, plus or minus 10%. Okay? This is how we can determine the value of resistance using this color code. Okay? Now, 10 raised to 3 ohm is nothing but 1 kilo ohm, correct? So I am writing here 47 kilo ohm plus or minus 10%. How would you find out 10% of this value? Very simple, multiply by 10 divided by 100. Okay? So 47 kilo ohm multiplied by 10 divided by 100 will give you 47 kilo ohm plus or minus 4.7 kilo ohm. When you multiply 47 by 10 and when you divide by 100, it will give you answer 4.7. Okay? that is 10% of this value, and that should be added and that should be subtracted. When you want maximum value, you can go for addition. When you want minimum value, you can go for subtraction. So, what will be the maximum value of resistance of this typical carbon resistor in practice? 47 kilo ohm plus 4.7 kilo ohm, correct? What will be minimum value? 47 kilo ohm minus 4.7 kilo ohm. Got it? Fine. If a fourth band is suppose golden, then for golden, come on, it is plus or minus 5%. How will you find out 5% of this value? Multiply by 5 divided by 100. Okay, fine. Now you may have question that how to remember this order, correct? I am showing you very simple way to remember this order. You can just remember first letter of all these words, okay? B. Roy. Suppose some typical fellow is there with the name B. Roy. B. Roy, okay? Goes to Bombay via Gateway of India on a good Sunday noon. The same sentence I have written here. B. Roy goes to Bombay via Gateway of India on a good Sunday noon. Out of this entire sentence, the letters which we require, I have just highlighted with pink color. Look, B. Roy goes to Bombay via Gateway of India on a good Sunday noon, correct? And from these letters which are written capital and with the pink color, you can just recall the corresponding name of color. Come on, black, brown, red, orange, yellow, green, blue, violet, grey, white, then golden, silver and none. Okay. For these three B, remember the order, don't get confused. First it is black, then it is brown and then it is blue. For this 2G, remember first it is green and then after it is grey. Okay. I repeat for the last time, black, brown, red, orange, yellow, then green, blue, violet, grey, white, then golden, silver and none. Okay. Same order is here. Got it? Fine. Now in textbook they ask one question. If you got a carbon resistor with value 1 kilo ohm plus or minus 10%, then how would you find out its corresponding color code? I am showing you. 1 kilo ohm means what? 1 kilo ohm means what? 1000 ohm, correct? 1000 ohm, can you rewrite? 10 into 100, can you write? 10 into 100. Now 10 into 100, 100 means 10 raised to 2, correct? So it is 10 into 10 raised to 2 plus or minus 10%, okay? For this value we require corresponding color code. Now 10 into 10 raised to 2, so it is 10 into 10 raised to 2. So you can just compare with this, then x will be 1, y is 0. X is 1, y is 0, so it is 1, 0, that is 10 into 10 raised to 2, okay? Plus or minus q, q value they have given 10%, okay? Now you can just write here, below x you can write 1, below y you can write 0, here below this you can write 10 raised to 2 and below this you can write plus or minus 10%, correct? So 1, 0 multiplied by 10 raised to 2 plus or minus 10%. Tell me, if you want x should be 1, if you want x value 1, what should be color of first band? It should be brown. If you want y value to be 0, what should be color of second band? It should be black. If you want 10 raised to n value to be 10 raised to 2, then for that what should be color of third band? It should be red. If you want q value to be plus or minus 10%, what should be the color of fourth band? It should be silver. So what should be the order of colors in that particular carbon resistor having value 1 kilo ohm plus or minus 10%? What should be the order? Come on, brown, then black, then red, then silver. Brown, black, red and silver. Got it? Fine. Let's go for question number 10. It is a short note on superconductivity. What is called superconductivity? I am showing you. there was a scientist with name Mr. Kamerlingh Onnes. Here I have written the complete name, Kamerlingh Onnes. In the year 1911, this fellow had proved practically that if you reduce the temperature of mercury, say when you make the temperature 4.3 Kelvin, at that time resistance of given quantity of mercury was found to be 0.084 ohm. And then after, when temperature was reduced further and when it was made 3 Kelvin, the resistance decreased drastically. It became very low as 3 into 10 raised to minus 6 ohm. And further, this fellow had proved that for mercury, when you decrease the temperature below 4.2 Kelvin, then its resistivity decreases very quickly to nearly 0. Tell me, at temperatures below this temperature, if resistivity of mercury decreases to 0 nearly, then what will happen to its electrical conductivity? Don't you know? Reciprocal of resistivity is called conductivity. Sigma equals to 1 upon rho. Rho is there in the denominator, and when it becomes nearly 0, 1 upon 0 would become infinite. So at that time, electrical conductivity of mercury would become nearly infinite, very large. Such a typical state of that mercury is known as superconductivity, and mercury itself is known as superconductor, correct? And this very temperature below which the material behaves like a superconductor is called its critical temperature, shown by symbol Tc, correct? For mercury, that critical temperature is 4.2 Kelvin. My dears, remember, this temperature is right now in Kelvin, and if in examination this same temperature is asked in degree centigrade, you know what to do. You have to subtract, if you want to find out answer accurately, you have to subtract 273.15 from this value, okay? And if you want approximate answer, then you may subtract simply 273. When you want to convert any temperature value from Kelvin to degree centigrade, you should subtract 273. Got it? Fine. Now just define critical temperature. A definite temperature below which the electrical resistivity of a given material becomes nearly 0 is called its critical temperature. I define again. A definite temperature below which the electrical resistivity of a given material becomes nearly 0 is called its critical temperature, shown by symbol Tc, correct? Last time, a definite temperature below which the electrical resistivity of given material becomes nearly 0 is called its critical temperature, shown by symbol Tc. Got it? Fine. Now, we have in laboratory many metals, then some alloys and some semiconductors which can attain a state of superconductivity. For semiconductors, just remember the examples: silicon, germanium, selenium, tellurium. These are the semiconductors on which, when pressure is increased, and it is increased to a very large extent, and when temperature is decreased considerably, at that time they behave like superconductors, okay? For decreasing the temperature, we take the help of liquid helium and liquid nitrogen. Liquid helium and liquid nitrogen, okay? Fine. My dears, here you just note one point. We find in laboratory that the critical temperature of oxide of some non-conducting material like ceramic is higher than critical temperature of some metals. What does it mean? It would be rather easy to obtain a state of superconductivity in case of oxide of ceramic, okay? Fine. And what is so far highest critical temperature obtained? It is for one compound made up of these 5 elements, mercury, barium, calcium, copper and oxygen. Out of these 5 elements, we have prepared one typical compound in laboratory whose critical temperature is the highest, and it is found to be 164 Kelvin. 164 Kelvin, correct? Fine. Now, from this point, you might be tempted to attain a state of superconductivity, because you may think this way, that once we achieve the state of superconductivity, at that time the resistivity is nearly 0 and conductivity is very large, then we can have flow of electrical energy for a very long time without wastage of energy. Yes, you are correct. But when you will get this state of superconductivity? Only when the temperature is reduced below critical temperature. And see the critical temperature value, it is very low. As compared to room temperature, it is very low temperature. And then to obtain very low temperature, again that technology is very costly. It would be rather very costly affair. For just saving 1 penny, you might have to spend 1 pound. 1 penny means economically its value is nearly 0, and 1 pound is right now nearly 100 rupees. That's why in English language there is a proverb, penny wise, pound foolish. Penny wise, pound foolish. When you try to save 1 penny, at that time you are showing your wisdom, correct? But at the same time, just to save 1 penny, you have to spend 1 pound. That is your foolishness, okay? So, penny wise, pound foolish, okay? So, you should not do that, correct? That is why scientists are trying to obtain the state of superconductivity, if possible, at room temperature, correct? So far, it is not achieved, but efforts are being done continuously, okay? Right now, the highest critical temperature obtained is, as I told you, for that compound made up of 5 elements, mercury, barium, calcium, copper and oxygen. And what is the critical temperature for that? It is 164 Kelvin, okay? Fine. My dears, remember, such a compound whose critical temperature is rather high is known as high temperature superconductor. High temperature superconductor, shortly it is written as HTS, okay? High temperature superconductor. Now, what are the applications of these superconductors in our day-to-day life? I am showing you. We use superconductors in case of thin film devices, the devices in which we employ thin films, okay? Then, to have transmission of electric power at very long distances. See, once you have a state of superconductivity, then you may have flow of electrical energy for a very long time, that too without wastage of any energy, correct? So, that would be rather preferable while just transmitting electric power at very long distances, okay? And then in case of high speed levitating trains, which are known as Maglev trains. In case of this Maglev trains, we have achieved the speed nearly 550 km per hour. 550 km per hour, okay,